and thank you for attending this CIE Tech Talk. I'll be talking about the Labtainers Cybersecurity exercises and that framework. If I can figure out how to move screens, there we go. Okay, so Labtainers is a collection of fully provisioned free cyber exercises. These exercises run all within a local VM or on a VM on the cloud. And we use Docker containers for efficiency and provisioning of the exercises. The lab exercises have automated assessment built into them. And so that lets you look at and assess student progress. And we are also able to individualize the labs to discourage sharing. The framework also includes a set of tools for creating, customizing, and deploying your own labs. So overall, we were looking to build a set of tools that let us manage experiential lab exercises. And the challenge or the problems that we were addressing are common problems that people encounter all the time in computer science education. Lack of infrastructure. It's difficult to actually maintain labs, all the provisioning that has to take place, all the debugging, things change underneath. There's a number of options in which students run labs on their own machines, but then you have to deal with different operating systems, libraries, that sort of thing. So you can end up with results that vary widely between student experiences. One of the other things we were addressing is the fact that when you're doing experiential type labs, you're trying to encourage all sorts of exploration and experimentation and even encouraging failure. So if that's what the student is doing, how does the instructor then go and assess that or understand how deep the student got into things or whether they even tried? And of course, the age-old problem of students sharing their results, either within the same class or over years. And so we saw a need to be able to individualize the labs. But if you do that, then potentially grading becomes difficult because now instead of grading 20 copies of the same lab, you're potentially grading 20 copies of different labs. And so we were looking to address those challenges in building Labtainers. So we wanted to create labs that were consistent and fair. All students would see the same thing. And the student and the instructors would have confidence that they're seeing consistent results from each student. As I said, we wanted to be able to parameterize the labs and make them unique so that it's harder, at least sometimes, for students to share their work. But we didn't want to have that creating labs of different difficulty for different students. Every student should have basically the same lab with just some different parameters. And then finally, the capability to automatically assess the student's progress. Now, this isn't necessarily automatic grading and automated determination of whether the student is A, B, or C. It's generally about the ability for the instructor to see that the student made particular goals or particular progress, and then potentially dig deeper into what it is the student did. And of course, this support for automated assessment is what makes parameterized labs possible. That is, I can have different labs for, or subtly different labs for a whole bunch of different students if I can automatically assess them and not have to drill down into each student's results. All right, so what we ended up with were standalone Linux-based cybersecurity labs. They do Linux, no Windows within the current set of labs. So each lab is potentially multiple components. You can have complex network topologies, and all the components are packaged together using Docker containers. And that gives us pre-configured execution environments in which we know exactly what's executing on the box, regardless of whether it's a Mac or a PC, what versions of systems are running. You can run these on Linux systems. And the point is you're always going to get the same execution environment. We can run these labs local to the student's computer. So typically what happens, the student downloads a single VM, and that's going to run many containers. So as a result, the student doesn't have to do any per lab provisioning. That's all done automatically. We also have a cloud-based option for Labtainers, which is relatively new, and this will run on either Azure or the Google Cloud platform. So here the model is the student sets up one of their free educational accounts. So this is something the student does. The instructor doesn't have to get involved, and the institution doesn't have to get involved. So for example, Microsoft makes student accounts available with free credits. They set up that account and then they build one of our VMs running a script. So it's all automated. And what the student ends up seeing is a VM desktop, but they see it through their browser. And this solves a big problem that's coming up that I'm sure a number of you have encountered when you're using VMs and things, and that is students are coming to school with the new Macs and they got M1 chips, and those don't run x86 VMs. And so everything that we've created is public, open, and we have a public repository of labs and an open framework. So look at all of these computers and routers on the screen here. You can run all of these on a simple laptop, all within one VM. And each one of those boxes shows up as a separate computer in the Labtainers environment. In reality, they each run as a separate Docker container, and we'll get into Docker container efficiencies in a little bit. But the point is you have a fairly complex architecture with a number of different boxes, each of which the student is able to SSH into, ping, explore as individual computers. And again, they're all running on a modest laptop. The web server that's in the left side, that in this example is a web server with a full LAMP stack. The workstations some of them might appear as CentOS workstations, others could appear as Ubuntu workstations. And this again is all automatically provisioned. All the networking, all the IP addresses are set up for the student when they start the lab. Of course, some of the IP addresses might change for some students. That's one way that we might parameterize the lab, in which the students, if they're trying to set up this DMZ, for example, they might be dealing with different IP addresses, and that makes it harder for a simple script to solve all the students' problems. Okay, so the magic that lets us run all of those boxes on a simple computer are Docker containers. So those of you who are not familiar with Dockers or containers, it's essentially namespace isolation. And the result is you end up with something that looks like a VM, but a whole lot less overhead. Docker is a commercial product with a huge, massive, huge user base, so it's not going to go away anytime soon. And it's a product that application vendors have been using for quite a while in order to deploy their applications in consistent environments. So it brings in all the libraries and all the configuration and all the etc files and everything else that you need to run a Linux application, and it packages them all up in a convenient way with Dockers. So we don't use Dockers that way. We kind of break the model in that each one of our Docker containers looks like and is a fully running Linux system with systemd, loggers, that sort of thing. So when the student gets to one of those Dockers, it looks like a Linux system. So a student laptop can then run many different containers. If you have an alternate system in which you're running individual VMs, you find that if you try to run 2 or more VMs on most laptops, they're going to start to melt. So again, we can have labs with many, many network components or labs with single components. It gives us that flexibility. And part of what makes all this work with Dockers is that all of those containers share the same Linux kernel. That's why it's so efficient. And that's why you're limited to Linux. But you're not limited to a single Linux distribution. You can have a variety of different distributions and environments as long as they're all sharing the same kernel. So since we are provisioning these things with Docker containers, that gives us total control of what it is that runs. And that makes it so that when the student is able to or starts up the lab, we automatically pull down the container images that are needed to run that lab. So if the lab has 5 different computers, it downloads 5 different Docker images. The containers are then created automatically on the student's VM, and we also create whatever virtual networks are needed for that lab. And then once the lab starts up, what the student is going to see are multiple terminals and or GUI applications starting up that they can then interact with. So the student is then interacting with multiple different computers, potentially, and each one is fully provisioned. And most importantly, or very importantly, we're able to instrument each one of those containers in order to record results. And we'll get to that a bit. Talk a bit about what I mean by parameterization. So this is an optional feature for different labs. Some labs have it, some labs don't. But it individualizes the lab for each student. And basically what we do is we generate a random number based on the student ID that they provide the first time they start up the lab. And a good example of how we do individualization is a buffer overflow lab. So the size of the buffer that needs to be overflowed in order to get control of a program affects what you do. And so if each student has a different buffer size, then they can't as easily share their solution. And the way we achieve that is we have symbolic replacement within the source code. And then the vulnerable program that the student has to be attacking is going to be compiled when the student first runs the lab. And that then is going to affect what you need to use as the return address offset. And we actually have written and published a paper on a variety of different approaches to parameterizing these labs, and that is published at that link there. So the automated assessment is achieved by collecting artifacts from what the student does. We make this, for the most part, transparent to students. Of course, if they poke around on their computers, they're going to see these things, but for the most part, the students don't see what's going on with the collection. It doesn't interfere with what they see. So most of what we achieve is done through bash hooks. And what that does is capture time-stamped copies of standard in and standard out. So if the student is running some program that they wrote or a program that we wrote that we're asking them to interact with, all the standard in and standard out is captured into timestamp files. And then we collect those files and forward those to instructors. We also are able to collect log files, that sort of thing, bash history. That's always useful in trying to determine what a student did. So we collect all that together into an archive, into a zip, and then the student forwards that to the instructor. The instructor then runs a tool that assesses the student performance based on expected results that the lab designer came up with. And so the instructor's tool consumes the artifacts that the student sends, compares those to the expected results, and presents the instructor with a table that shows the progress of the student. Did the student achieve selected goals? And again, this automated assessment makes individualization of labs practical. Looking at that buffer overflow lab example, even though every student's doing a different buffer size potentially, the automated assessment looks to see, did the student get control of IP, and were they able to run a shell? So within Labtainers, there's sort of three roles. There's the designer. That's the person that puts together the lab and decides what's going to be in it. That can be the instructor as well, or it could be some other subject matter expert. And then we have the instructor. That's the individual that assigns the work to the students, picks what labs they want the students to do, make sure the students have the background necessary to do the labs. So the labs in general are not entire curriculum packages. We don't teach you about stack structures and such in order to do the buffer overflow. It's assumed that the student has background in that from instruction. And then finally, there's the student. That's the person, of course, that does the lab. So what does a student do? What do they see? So most students just install a VM or they create one on the cloud. So installing the VM is just downloading it from our website and bringing it into VirtualBox or VMware. The student then performs the lab as directed by the instructor. When the student finishes the lab, the artifacts are automatically collected into a zip file, and the student sends that zip file to the instructor. And that can be done through a learning management system or email or whatever your preference is. And we do have support for a couple of learning management systems so that you can bulk download the results from all your students and assess those using our tools. So here is a screen that illustrates what a student might see when they start a lab. So this is the Linux desktop that they see from which they start all the labs. At the top there, you see that they typed in the Labtainer telnet command that says, hey, I want to run the telnet command, telnet lab. Next things you see are that the system is pulling the Docker images it needs from Docker Hub and bringing them into the student's computer. In this particular lab, there's only 2 computers. Student then provides or confirms the email that they want to use just as a simple identifier. We don't use the actual email address for anything other than as an identifier. And each lab has a lab manual, and that next line, the lab manual, that link, student can click on that link and open the lab manual, which is typically a PDF file. So it's all kind of centrally located off of this desktop. They then press enter to do the next, or to actually start the lab. And the next thing they're going to see in this particular lab are 2 different terminals. One terminal is connected to the server computer, one is connected to the client. And if the student explores, which we encourage, of course, they see that they are 2 different computers. They get different IP addresses. I can ping one from the other. They're configured differently. And so the student interacts with those terminals, performs the lab per the lab manual. And then when they finish, they provide the zip file to the instructor. I will point out that this automated assessment that I keep talking about, that's of course optional. A lot of instructors that use Labtainers, they don't do the automated assessment. They have their own lab report strategy format in which they ask the students to prepare lab reports, and that's fine. The automated assessment isn't necessary. It's there if you want to use it. Okay, so what does the instructor do? Instructor collects those zip files together into a directory and runs our tool that creates a table of student progress. So the table has a row for each student and a column for each of the goals that were identified by the lab designer. We also include an optional browser-based deep dive into student activity, and we'll see an example of that. And the artifacts that we collect might include lab reports. So on that desktop or in the student's environment, you can have them create a lab report, and that would be included in the artifacts as well for the instructor's review. So here's what an example automated assessment looks like. Again, this one is for the Telnet lab. You see the table has a line for each student and then 3 different goals in this particular rather simple lab. And there's usually a key that tells you what the goals mean. So we have the three descriptions: fail, login, telnet view, and SSH view. And then you have the option to point your browser to that link that's there. And if you open that link, you see this next screen, your browser pops up, and that gives you the opportunity to take you to the table of the student goals, let you see the lab manual, that sort of thing. The student goals looks just like the table that we already saw already. Except it's an HTML format, and each one of those entries is a link. And so the student or the instructor, I'm sorry, is able to click on these links and delve deeper into the actual results that the student got. So if I click on a student name, for example, I'd be able to see their bash history. If I clicked on the other ones, I would see what goes into those results, and that those results might be looking at the standard out of a telnet session, for example. I can actually see what the student had done. Okay, so we currently have over 50 labs, and they really run the gamut of cybersecurity topics. We have a number of software vulnerability labs, including buffer overflow labs, looking at things like printf. A number of networking labs, including ARP spoofing, DNS spoofing. We've got labs that include routers. We have, with real border gateway protocol routers that students can interact with. A number of operations-based labs in which students are dealing with things like ACLs and system logs. There's also host-based IDS type systems that they can interact with. Authentication systems like Radius and LDAP. A number of web labs, including labs that highlight cross-site scripting. And there is a set of iModules, which I'll get into later, but this set of iModules was created by a different developer. And these cover OWASP web security topics. And there's 10 of those available as well. A number of different cryptography-based labs, including deploying simple VPNs and looking and exploring hashing. Suppose some of you are probably hearing the jet going by. So we'll pause for just a moment. Okay, and then finally, we've got a whole suite of labs that address industrial control systems. They include PLCs, we've got the soft PLCs, and simulated PLC environments. So we've got all those labs, and that sort of begs the question, how do the instructors or the students find labs that they want to run? And so we've developed a number of tools that help you do that. The first one is keywords. So if you run the Labtainer command and ask to see a list of keywords, you'll see a list of keywords like you see on the top of this terminal screenshot. That's the end of the list. But so you'll have keywords like SSH, SSH agent, TCP IP, and you can then say, find all the labs that include one of the keywords. In this case, SSH is what I asked for, and I see that there's 4 labs that have that keyword. Another way that we have of finding labs and organizing labs are something we call Labpacks. So a Labpack is nothing more than a collection of different labs that are managed together or have some common theme. So we've defined a set of initial Labpacks, but the instructors are able to define their own Labpacks if they've got a set of labs that they want to make part of their course. So in the default case Labpacks we've broken them into those categories: networking, introduction, networks, operations, crypto, access control, net traffic, web security, software vulnerabilities, and industrial control systems. So we've packaged together all the labs that fall into those categories into those individual lab packs. And the student can then choose to do a lab pack or be told to do a lab pack. And as they run the labs, the system keeps track of which ones they've done and tells them which is the next to do. And again, this is available for instructors to package together their own sets of labs. So each lab has a lab manual, as we've seen, and that's primarily for student reference in performing of the lab. Most of the labs that we have include automated assessment. And as I said, you don't have to make that part of what you do, but it is there, and it's also there for students to access if they wish. So we have something we call check work, in which the automated assessment is performed, and the student can see whether they've achieved the goals that the lab designer has set out for that particular lab. We also have something in the form of interactive quizzes, and there's a couple of labs that use these quizzes, and the quizzes are not they're not really intended to assess after the fact what the student learned. It's actually more intended before the lab. So an example of the use of this quiz would be in our database lab. We've got a lab in which the student is responsible for understanding a security policy of an organization and then enforcing that security policy by configuring the database. So if you think of that problem, it's important that the student actually understand what the policy is before they go about setting permissions on tables, because they can spend a lot of time setting permissions on tables. And if they don't know what they're trying to achieve, they're not going to learn anything, and they're going to get frustrated, and it's just not going to get anywhere. So the key in that particular example is that the student understand what the policy is first. And that's something they got to sort of get their head around before they start interacting with the actual lab. So that's what that quiz does, is it points them to the lab guide that tells them what the policy is, and then asks them a series of questions. So the student can have some confidence that they understand what the policy is before they go about trying to implement it. And then finally, each lab, or most of the labs, have solution scripts. So we don't have formal instructor guides for most of the labs to tell you how to do them. But we do have automated scripts that we use for our regression testing that basically show you how to perform the lab, or how to perform most labs. And these scripts are in the form of command lines and mouse interactions for GUI-based labs. So most instructors find those useful to understand how to go ahead and perform the lab. Okay, we include a number of tools that help you create new labs or customize existing labs if that's what you'd like to do. So we now have a GUI-based tool that we'll see an example of in a second. And with this tool, you are able to provision each one of the containers that is going to be part of your lab. That is, define what the files on that computer are going to be, what packages are installed, that sort of thing. With the tool, you're able to define network definitions, define what the networks are, what the different computers are going to be hooked up to those networks, what their IP addresses are, that sort of thing. The tool then, when you run the build command on that tool, it is going to create the set of container images and configuration files that are needed for that lab, and lets you then test and exercise the lab. And then we have tools that let you publish your lab as something we call iModules. And so iModules are instructor created labs that you can then share with not only your students, but other institutions if you so choose. So you would, after you publish your iModule, you would send me a link to your iModule URL, And we can add that to the web page. Currently, we've got that one set of iModules for the OWASP web security labs that I referred to earlier. You can also use these tools to customize an existing lab to do it your way. Or if you just want to change one of our lab manuals, the manual that the student sees by clicking that button, if you want that to be your own version of that lab manual, that's easy to do as well. And again, you can use iModules to do that. So your student sees what you want them to see in the form of a lab manual. So this is what the lab editor looks like when you open up for a particular lab. You see this is the Telnet lab that we've used as an example in this presentation. It has the two containers, client and server, some network, and then over the right, you'll see the buttons that let us define the automated assessment and parameterization. So if I click on one of the containers, I would get a window like this that lets me configure that container. In this case, the only really interesting thing is I'm connecting it to a network. So down at the bottom there, I see I'm connecting it to a network. If I wanted to add a different username, password, I can do that. And I can organize the terminals that pop up that the student sees using this as well. So one of the key things that you're doing when you're defining a new lab and defining a container within that lab is you want to decide what software packages are going to run on that container. So we have a number of different base containers that you can start with. These base containers represent things like a simple workstation, a network-based system. We've got base containers that include Wireshark, base containers that include Firefox, that sort of thing. So you would pick a base container and then you add other packages to it based on what it is you want to do with your lab. And so if you look at this, this screen here, it shows something that's called a Dockerfile, which is the standard file used by the Docker system to do provisioning of the containers. So the file is automatically generated. You don't have to do anything with it. But if you want to add packages, you would open up this file, and this rectangle that I've highlighted here shows the one area of the file that you would edit. And to anybody that's worked with Ubuntu type systems, you'll see that I'm adding a package. And in this case, I'm adding the Telnet D package. If what you're doing is configuring a CentOS type system, then you would see Yum, and you would use Yum to add whatever packages you want to this particular, or to your particular container. Okay, so you would edit that and then tell the system to build it, and it's going to build and let you test your lab. So here's a quick example of the automated assessment identification of artifacts. So again, this is for that Telnet lab, and I'm identifying 3 different artifacts here. You can see on the first line, it says this artifact is going to exist on the client container. And you see under file that what this artifact is looking at is the output from running the telnet command. In the second line, you see that the artifact is the output from running the SSH command. And then on the final line, you see the file is not output from any particular command, but the actual log that comes for authentication on a Linux system. So I won't go into the details about the field types and such, but we've got a fairly rich syntax for identifying different artifacts and then comparing those artifacts to expected results. And again, we've got a lab designer guide that goes into how to do all of this in detail. Okay, so we have a web page, of course. That's our link there. That's where the students would go to get the VM appliance, and there's a whole lot else there as well. if the student wants to use the cloud-based system, they would go to the student guide, which they can find on that website. And that has detailed instructions on what scripts to run and how to go about creating your own Labtainers VM on either the Azure or the Google Cloud. Our website includes a number of video tutorials on how to go about installing Labtainers and use Labtainers. And there's also a tutorial video on how to use the automated assessment. You'll find copies of the student guide, instructor guide there. And the lab designer guide that goes through detail, including tutorials on how to build your own lab. We have a link to the iModule page, and so you can go there in order to get those OWASP labs. And essentially what that looks like is you copy the URL that's there, and you enter that URL into your Labtainer instance, and you tell your students, here, take this URL and enter it into your Labtainer instance. Once they've done that, all those labs are now then available to them. They just have to name them and run them. The website includes a number of published papers that we've have over the years on Labtainers. And Labtainers is open source on GitHub. So that link there gets you to our GitHub page, and that is the preferred way of identifying questions and issues with Labtainers. Go to the Git issues and fill that out, or just email me. That works as well. Yeah, so if you have any questions or problems with the deployment of Labtainers, either the GitHub issues or just write me directly. Okay, I guess that's pretty much what I had to cover. I'll answer any questions if there are any.
All right. Yes, I think there were some questions that come up in the chat. So this was great. Thank you so much, Mike, for presenting this. There was a question that stated, is there the possibility to calibrate the models? Example, BNR of networks.
To calibrate the model.
And again, feel free to type your questions in the chat, or you can unmute yourself if you need to provide clarification on your questions or just want to ask your question.
Yeah, I'm not sure I understand that question.
Okay.
Halim,
if you want to unmute yourself, you can unmute yourself.
Hello.
Parameterizing the model.
Oh, hi.
Yes.
Thank you for the presentation. What I meant by let's see, calibration is, am I allowed, for example, to modify the different parameters of the model in terms, for example, you spoke about the stack, the size of the stack, or the number of computers that I can have that are linked to the network, or for example, the bandwidth. Am I able to modify these or not?
Well, you can create the lab to contain whatever you want. If you're talking about parameterizing it so that each student sees something different, then it's whatever, and you use your imagination, it's whatever configuration values you want to change. And that configuration value can be a value within a file. It can be of value within our configuration files. So for example, if you want to dynamically change IP addresses so that students get different IP addresses, that's how you would do that. And so, anything that you can change within the running computer, you can alter with our parameterization.
Okay, thanks. Thank you.
Okay, so we have another question. Docker in general focuses on application containerization, while LXC on OS containerization. Since your work breaks the limitation and puts the whole OS in a Docker container, why not use the LXC instead of Docker?
Yeah, it's a good question. I guess it's because Docker had a richer set of tools for us to use. It was better documented at the time. And yeah, overall, it was just easier for us to get going. We actually started with LXC as we were many years ago delving into how to go about doing this. And just things like the Docker Hub and such, it just made this all so much easier.
Just a quick question, follow up that,
Yeah.
because we are trying to doing something like that, with the LXC. So I would just wonder, like, how complicated you break the limit to put everything in Docker is kind of easy.
Yeah,
or
it's
hard?
not, so yeah, it breaks their model, but it's not hard, and it's not disruptive. It just means that we find, and this isn't anything we invented, people have built Docker images that include systemd, and they have worked examples how to do that. So we just go ahead and do that. We use, so where a normal application, their Docker image is just going to have their application and maybe a few supporting applications and libraries. We just throw in systemd and the RLogger and everything else that's part of that standard Unix distribution, so that including help files. If you go to a normal Docker container and you run man, it's just going to look at you, but we throw the man pages in there as well.
And another question, have you guys tried like putting like a Kali or like Parrot into this kind of container?
Yes, so there's one of our labs is a Kali and a Kali lab that runs Metasploit. And so yes, those tend to be fairly large containers because of all the stuff that they pack into them. But it's doable, so we've got the worked example, and it's a fairly popular lab.
Oh, okay, that's great. And you also have the GUI interface using VNC or
yeah, right.
all like command line interface. So the user
No, there's GUI.
directly.
Yeah, so there's
GUI.
GUI.
Okay.
So if you're running on a VM that's local to your laptop, if you start up Wireshark in one of your containers, you see that Wireshark, and you're using your if you're running on that VM, you're using the VM's X for the display. When you move to the cloud-based systems, so the students interacting with a VM in the cloud, what happens there is we do run VNC, as you guessed, or the no VNC. And so we basically have a container that does nothing but run the X services and provide the desktop. And then when our main container, which runs Docker, opens its windows or opens its terminals on that display. And so what the students then sees is the no VNC desktop with the terminals as they're created and needed. So in that environment as well, you can run GUIs.